Okay, great. Thanks so much, Kazam. Let me thank all of the organizers for the invitation to talk at this nice meeting. I think it's great to get together people all sort of thinking about ideas related to holography to kind of discuss common ground. So today I'm going to try to tell you a little bit about kind of a boundary holographic-like viewpoint on the physics of inflation in the early universe. And I will mostly be talking about work done in collaboration with this fantastic set of collaborators. So let's start. Maybe just to start, I kind of want to point out this sort of curious fact that the arrows that realism, or the directions that sort of realism and understanding go on this sort of plot to go in opposite directions, in the sense that the asymptotics that we understand best from the perspective of holography are the ones which are the least realistic. And sort of, roughly speaking, in ADS space, we understand the exact rules about what sort of constraints boundary observables should satisfy. We sort of have non-perturbative information about the constraints that conformal correlators should satisfy. And from this, we can infer something about quantum gravity in ADS. In flat space, the situation is a little bit worse. The sort of holographic observable is something like the S matrix, and there we understand very well, sort of in perturbation theory, to some loop order, what sort of things can happen, and we have some handle on some version of holography in flat space, which I hope we will discuss more. But in de Sitter space, we have very, very incomplete understanding. So as I'll try to illustrate to you, we sort of are just starting to understand what's going on at tree level. And I'm going to focus in this talk on the physics of inflation, so this putative period of de Sitter expansion in the early universe. But we also have very strong evidence that we are headed to a late stage of de Sitter expansion. And so it's very important for the world we live in to understand holography in these kind of spacetimes. Okay, and so very roughly speaking, the philosophy I'm going to take is the fact that we don't directly see inflation, we merely infer its existence. I'm going to take as a hint that maybe we should try to think about inflation from a holographic perspective. And let me also say, please feel free to interrupt me. I know we're kind of like straddling the Zoom and post-Zoom era, but please try to interact. It'll make it more fun for everybody. Okay. So let me just sort of take a step back and remind you about why we like inflation, why we should try to think about inflation holographically. Let me try to motivate that for you. And so sort of at zeroth order, cosmology is a study of correlations. We don't get to build universes in the lab and do experiments. All we can do is we look out in the sky and we just sort of see objects in the sky. We see stars and galaxies. And what we can do is we can ask about how the positions of these objects are correlated with each other. And sort of there's a remarkable fact that the galaxies we see in the sky are not randomly strewn about, but their positions relative to each other are actually correlated. Okay, and sort of we can capture this information in statistics of the distribution of these objects. So this is just a plot of like the galaxy power spectrum. So the 2-point function about positions of the galaxies. Okay. And what we do in cosmology is we trace these correlations across time. And by doing this, we infer something about the dynamics and the evolution of the universe. And so we can trace the correlations that we see in the late time large scale structure all the way back to the CMB last scattering surface, where the correlations are seen in temperature anisotropies of the cosmic microwave background. And those have some associated power spectrum as well. And what we can do is we can trace these correlations all the way back to sort of the beginning of the hot Big Bang. So this thing that I'll call the reheating surface. Okay. And there's also this interesting fact that as we go further and further back in time, sort of the correlations get simpler and simpler. And so the 2-point correlations on this reheating surface at the beginning of the hot Big Bang are extremely simple. They're described by a very simple power law. But nevertheless, they're kind of peculiar. They're kind of peculiar because if you really take the correlations at face value, they look acausal in the sense that points on the sky that have never been in causal contact are nevertheless correlated. And so we have to explain this kind of peculiar effect. So we want to explain the origin of these correlations. And of course, this puzzle has a simple resolution. The simple resolution is really just that the hot Big Bang cannot be the beginning of time. There had to be some pre-Big Bang epoch during which these correlations were generated. Okay, and basically this pre-Big Bang epoch is what we call inflation. And so inflation explains in a natural way how these perturbations could have arisen causally. And roughly speaking, what it says is, okay, the hot Big Bang is not the beginning of time. Instead, there was some pre-Big Bang de Sitter phase where these correlations were generated, and the hot Big Bang is really the asymptotic future boundary of this de Sitter-like space, okay? And a very interesting theme that will kind of recur in this talk is that the properties of the geometry of this space, this pre-Big Bang phase, get encoded in the statistics of the fluctuations that we see on this late time reheating surface. Okay, so here's a very, very simple example. So I told you the correlations, that sort of the 2-point correlations that we infer on this reheating surface are extremely simple. They're sort of a simple power law, which is very close to being scale invariant. It turns out that this near scale invariance of the 2-point function can be thought of as a consequence of the near time translation invariance of inflation. And so this 2-point statistic is really capturing something about the invariance of the geometry under time translations. And so it's kind of nice. Something about time evolution is getting encoded in a way that makes no reference back to time or even space-time. Okay. So if we want to really learn something about the microphysics of inflation, we need to extract information about higher point correlation functions. So this simplest thing I told you about the 2-point function is really a consequence of kinematics. Like if you thought of writing down some effective field theory description of inflation, the 2-point function is really controlled by the sort of free part of the effective action. And this thing is just controlled by symmetries. And so the 2-point function is only telling you about kinematics. If you want to know about the underlying microphysics, you need to probe the interactions of the inflaton, or you need to probe higher point correlations between fields evolving in the inflationary spacetime. And so that's going to be mostly what I want to talk about today, is how we can extract some information about higher point functions from a boundary point of view. So I understand that this is not really, phenomenology is not really the focus of this workshop. And so for this audience, it's maybe not the most interesting aspect of this story. But something which is interesting about the physics of inflation is that it could have taken place at extremely high energies. And because there's so much energy in the background inflationary expansion, it can produce very heavy particles on shell. And so there's a tremendous amount of promise of using inflation as sort of a large particle collider and looking for the signatures of heavy particles that were produced during inflation in these observables that we see on the reheating surface. And just for numbers, it's the energy scales are astronomically larger than anything we could ever hope to produce on Earth. And so there really is some promise of having some large physics reach using sort of precision measurements of inflationary correlators. Okay, so that's just some phenomenology motivations. Okay, so there's another very interesting feature of the inflationary geometry that gets encoded in the statistics of late time correlations, which is that, so if I imagine thinking of the late time correlations on this reheating surface as a function of the spatial points, or in Fourier space, a function of the lengths of the various momenta involved in a correlator, as I change the distribution of spatial points, or I change the momenta involved in a correlation function, I'm really probing different epochs during the inflationary expansion. And this is really just because of the physics of de Sitter space. So modes of different wavelength freeze out at different times in the cosmological history. They sort of pass the de Sitter horizon at different points in time. And as I change the shape of a boundary observable, if I imagine, so for simplicity, let's imagine we think about a 4-point correlation. at late times that arises from the production of some particle on shell, which then decays. As I change the shape of this boundary quadrilateral, which the correlation is a function of, what's going on is the bulk particle that produced these correlations is propagating for different distances in the inflationary spacetime. And so I'm really probing different time delays between these two interaction vertices in de Sitter space. And so the time dependence of de Sitter gets translated into some dependence of the late time 4-point function on the shape of this quadrilateral. So it gets translated into sort of the dependence on the scale here. Okay, so an important thing I want to emphasize, which I already mentioned, is that we don't have any direct observational access to the inflationary epoch. Because the universe thermalizes at the hot Big Bang, it's very difficult to sort of look past periods of thermalization. And so instead what we do is we infer the existence of the inflationary epoch by looking or inferring these correlations that are imprinted on the late time reheating surface. And so inflation is sort of a story we tell ourselves to explain in a causal manner where these correlations came from, okay? But the fact that we don't directly see inflation, we can sort of think of it as a machine that generates objects consistent with principles that we like, suggests that maybe we should take a different perspective on inflation and just ask whether we can directly construct the final observable on this asymptotic boundary without ever making direct reference to the inflationary time evolution. Okay, and so that's sort of the viewpoint that I want to advocate and explore. And it's sort of a roughly holographic viewpoint. We want to talk about the physics of inflation without ever talking about the inflationary spacetime. Okay. Okay, and so in order to begin to address this question, so I apologize, but I'll only have answers for, or at least partial answers for how to do this in perturbation theory. So I'm going to be talking about constructing perturbative correlation functions in de Sitter space from sort of this boundary perspective. And in order to start to do that, the question that we have to ask, or that we're confronted with, is like, what are the rules that a consistent boundary correlator has to satisfy that comes from local causal time evolution? We sort of want to understand this question. And that's sort of the question that we've been exploring for the last few years. And there are many other people exploring similar questions. In particular, like Enrico Pyer's group at Cambridge, I see many of our friends in the audience. They've been also doing a lot of interesting work on this question. Okay. So here's sort of an outline of what I'm going to tell you about today. So first, I'm going to review the singularity structure of cosmological correlators. So I'll explain in a minute, but we're going to try to abstract some lessons from other holographic or bootstrap programs and try to apply them to cosmology. And one lesson that we like is that the singularities are very powerful in organizing the structure of correlation functions. And so I'll try to explain a little bit how that works. And then an interesting fact is that you can think of the challenge of time evolution, or understanding the time evolution in de Sitter space, as getting translated into understanding how to deform correlators away from these singular points. And so I'll explain some ideas about how one might go about reconstructing correlators, only knowing information about their singularities. And then I'll just kind of conclude with some summary and vague speculations. Okay. All right, so maybe now is a good time to stop and ask if there are any questions about sort of this motivational stuff. All right, everybody is super on board. That's great. All right, good. So let's start talking about the singularities of cosmological correlators. And so here I want to sort of draw a lesson from the S matrix. And the lesson I'm going to choose to draw, there are sort of many lessons that one could draw, but the one I'm going to abstract is that much of the physics of scattering amplitudes is controlled by singularities, at least at tree level. And what I mean by this is that we sort of know where all the singularities of the tree level S matrix are allowed to be, and we know what their properties are. So for example, we know that tree level scattering amplitudes, the S matrix factorizes when intermediate particles go on shell. So if I have some scattering process and I have some of the momenta add up to the mass of a particle in the spectrum, what happens is the amplitude splits into some lower point functions connected by some propagator. And physically what's going on is like I'm producing a particle on shell, it's propagating a long distance in space-time, and so the processes are effectively factorizing. And further, we know that the residue of this pole where a particle goes on shell has to be positive by unitarity, and we know that the residue is also given by these lower point amplitudes. Okay, and it turns out that if I just tell you these facts, in many cases, you can reconstruct the full S matrix just from this information. So for example, for massless spinning particles, you can basically reconstruct the entire tree level S matrix from this simple information. It's very constraining. And also the singularity structure is very powerful. It's a very powerful handle on loop amplitudes and stuff like that. So I want to sort of abstract that lesson. I want to first focus on singularities and then understand how to extend the object away from these singular points. So in the context of the S matrix, this is an extremely powerful viewpoint and you can get very far. And so we just want to see how far we can get in cosmology. Okay, so first I have to, before talking about the singularities of the object I'm interested in, I have to actually introduce to you the object that I'm interested in. So fundamentally, the objects that we observe are correlation functions, but I'm instead going to focus on a slightly more primitive object, which is basically the cosmological wave function. And you can think, roughly speaking, of this as being like the state of the quantum field theory on this late time surface. And if I have this object, I can compute any correlation function I want. So it's sort of like a slightly more primitive object than a correlator. Okay, and it's sort of just defined in this simple way. So it's really the projection of the interacting vacuum onto the set of Heisenberg picture eigenstates of the fields that I'm interested in. And so for simplicity, let's just imagine I have a fixed background for now. I have some fields propagating in it. I'm going to take their vacuum and project it onto the set of field eigenstates. And so this defines some wave functional, which is now a function of the field profiles on this time surface where I'm trying to compute it. And the reason that this is an interesting object to compute is that it provides a probability distribution for field profiles on this time slice. And I use it the same way that I use the wave function in quantum mechanics. So if I want to compute a correlator like this, what I do is I just square the wave functional, multiply by a bunch of fields, and integrate. Okay. In perturbation theory, so again, I'm going to really only be telling you things in perturbation theory. In perturbation theory, there's sort of a algorithmic, systematic way of computing this wave functional. And roughly speaking, we're going to exploit the fact that the wave functional is effectively the on-shell action evaluated on some classical solution with prescribed boundary data. And so roughly speaking, I'm going to evaluate the action on a solution that interpolates between the vacuum that I'm interested in the past, and then some field profile on the time where I'm computing the wave function. And then the on-shell action is a function of this late time field profile. And so that makes it sort of a functional, and that functional satisfies the Schrodinger equation. So in perturbation theory, it's natural to expand this wave function in the following way. So I think of it as the exponential of some object that depends on field fluctuations. And then sort of order by order in perturbation theory, the wave functional is dependent on these sort of kernels that tell me how the field fluctuations at late times are correlated with each other. Okay. And it's really these objects that we want to compute, these objects that are called wave function coefficients for sort of obvious reasons. And the nice thing about these wave function coefficients is that they can be computed in a simple Feynman diagram expansion. Okay, so there's like, if I want to compute the 4-point wave functional coefficient, I compute it very similar to the way that I would compute 4-point scattering amplitude in quantum field theory. Okay, so that's a little bit abstract. I think the easiest way to kind of make your peace with the wave function is to just see some simple examples where we compute this. And so here I'm just going to give you sort of the simplest possible example where you could imagine computing this ground state wave function. The toy model is really just a a massless scalar in flat space with some polynomial interaction. And for simplicity, let's just think of some phi cubed theory in flat space. And so remember, what I want to do is I want to construct a classical solution with some particular boundary conditions. And it turns out that there are well-defined perturbative building blocks that do this for you. It's kind of like, essentially what we're doing is the same type of thing that you do when you compute the partition function in ADS-CFT. There are two types of propagators, exactly like in ADS. There's this bulk to boundary propagator, which is really just some free plane wave like solution. And then there's also this bulk to bulk propagator, which is slightly peculiar. So this is sort of where we put in the information that we're computing a wave function rather than some boundary correlator or something. And the important thing about this bulk to bulk propagator is that if I drag one of the points to the boundary, this bulk to bulk propagator vanishes. And so this thing is responsible for imposing the boundary condition that tells us that we're really computing the wave function. Okay, and then there's just some vertex factors, which you get in the usual way, like you would in a scattering amplitude calculation. Okay, so once you have these perturbative building blocks, you just combine them together in the way that you normally would in QFT. So if I draw some diagram like this, to an internal line, I assign this bulk to bulk propagator. To an external line, I assign this bulk to boundary propagator, put in the vertex factors, and then these interactions can take place at any point in time. So I have to integrate over the time insertions of these two objects. And I should have mentioned, but I'm going to work exclusively in Fourier space because the spatial slices will always be flat R3s. And so it's a natural thing to do to go to Fourier space. Okay, so there's sort of an important fact about cosmology is that time translation invariance is broken, and so energy doesn't need to be conserved. And so these objects depend on strictly one more variable than a scattering amplitude, which is the total energy involved in the relevant process. Okay, so again, that was maybe a bit abstract. The easiest thing to do is to just write down some examples. So here's the simplest possible example. Let's compute the phi cubed 3-point wave function coefficient. It turns out, it just has one factor of the bulk to boundary propagator for each leg. Then I have to do a time integral over the possible insertion point. So it just gives me some expression like this. And it turns out the corresponding wave function coefficient is just 1 over the total energy involved in this process. Okay, and just as a reminder, the corresponding flat space scattering amplitude would just be a number. It would be like the coupling constant associated with this interaction. Okay, so only slightly more complicated than that is like the simplest exchange diagram. So I can imagine computing the 4-point function using this perturbative approach. So now I have to assign a bulk to bulk propagator to this internal line. And now I have to do 2 time integrals, and I have to integrate over all the possible time orderings between these vertices corresponding to these theta functions. So it's slightly more complicated, but again, totally doable. And what you get is this following answer. And notice it depends in sort of a simple way on the energies of the external particles. So there's one factor, which is sort of the total energy involved in the process. And then there's one factor, which is the energy flowing into the left vertex, and then another factor, which is the energy flowing into the right vertex. Okay. Okay, and so from this, we can already kind of abstract a lesson, which is that correlation functions are singular when energies flowing into a vertex or really flowing into a subgraph add up to 0. Okay. And it turns out that actually this is a totally general phenomenon. Okay. And so that's sort of the takeaway message, but here I'll try to justify why that is the case. So roughly speaking, if I have energy flowing into some subgraph, there's some singularity. And in fact, you even know what the residue of that singularity is, as I'll explain. But here, let me try to justify why that's the case. So first, let's think about this total energy singularity. So let's imagine we analytically continue the energies such that the total energy involved in the process adds up to 0. So this can't happen for physical kinematics, but I can imagine going off into the complex plane and having the total energy add up to 0. So you can imagine trying to compute. Okay, yeah, sorry. So let me say it a different way. So if I have some, let's think about a contact-like diagram first. So for each external leg, there's a plane wave, which is the bulk to boundary propagator. And I can ask where, so the corresponding wave function coefficient is given by an time integral like this. And I know that this thing should be singular when the total energy adds up to 0, but you can ask where is this singularity coming from? And it's really coming from the fact that this lower limit of integration is in the infinite past. So the domain of integration is going to infinity. And when the total energy adds up to 0, there's no oscillatory suppression in the infinite past. And so something diverges. Okay. So that already sort of tells you why there should be some singularity. But more interestingly, the coefficient of this singularity is a scattering amplitude for the exact same process in flat space. Okay. And the easiest way to understand this is that if we were computing a scattering amplitude, what we would do would be we would integrate all the way from -infinity to +infinity. And what we would get would be a delta function enforcing energy conservation. Instead, here we're integrating sort of over the half space. We're only integrating from -infinity up to some time t, which here I've set to 0 without loss of generality. And so instead of getting a delta function, what we get is a pole. And so this singularity, as e goes to 0, its coefficient is really the same calculation that we would have done if we were computing a scattering amplitude. And so just on general grounds, we should expect the coefficient of this total energy singularity to be the corresponding scattering amplitude. And another way to think about it is, roughly speaking, when we're computing a wave function coefficient and when we're computing a scattering amplitude, the calculation is almost exactly the same, except we don't Fourier transform in time. And then instead of integrating over the full time interval, we only integrate over half. And so it shouldn't sound outrageously surprising that the coefficient of this singularity and the flat space scattering amplitude are related. And so this is kind of another interesting feature of wave function coefficients, is that these wave function coefficients really can be thought of as a one parameter family of deformations of scattering amplitudes, that when you go to a particular locus in kinematic space, you recover the scattering amplitude, but they sort of have a life of their own away from this special point. And so that's kind of an interesting fact. Okay, so correlators that arise from contact-like interactions in the bulk only have this total energy singularity. But correlators that arise from more complicated bulk processes also have other singularities. So for example, a correlation function that arises from exchange, there are two interesting points in energy space. One is when the total energy adds up to 0. And the other one is when the energy involved, like in an interaction vertex, adds up to 0. And it shouldn't be particularly surprising that when the energy at an interaction vertex adds up to 0, the wave function is also singular. And in fact, we also know the residue of that singularity. It turns out, unsurprisingly, it's related to the amplitude associated to this 3-point interaction, because you can kind of think of it as being similar to the argument I just gave you, that the calculation we're doing involving this left vertex is essentially the same as doing some 3-point scattering amplitude calculation. But then the other important thing is that just from the structure of the bulk-to-bulk propagator, another way to think about it is that the singularity of the wave function when the left energy adds up to 0 is coming from very early times, where this left vertex is much, much earlier than the other interactions in the process. And so we can effectively replace the bulk-to-bulk propagator with its this time goes to -infinity limit. And from the structure of that object, we see that what we're effectively doing when we integrate over the right time is we're computing the difference of two the difference of two wave functions, one evaluated at positive energy and one evaluated at negative energy. And so, if we define this kind of shifted wave function object, the residue of this partial energy singularity is just the product of a flat space scattering amplitude in this kind of peculiar shifted wave function object. And the details of what this residue is are not extremely important, but the important fact is that we know where this object should be singular, and we know what the coefficient of this singularity is. Okay. And another interesting fact to emphasize is that the existence of these partial energy singularities is already a signature of exchange in the bulk of some tree level exchange. And so, for example, if you handed me a correlation function and you said, I claim that this comes from the exchange of some particle in de Sitter space, and it didn't have any of these partial energy singularities, I would be extremely suspicious of your claim. So it's already interesting information that we can extract some amount of physics from the existence and locations of these singularities. Okay.
Sorry, Austin. Why do you always have S channel and never T or something else? Is there a reason for that?
Yeah. So this, I just wrote the S channel just for simplicity.
But you have the other ones as well.
Well, in this, it's a little bit dependent upon the exact theory that you're interested in. So here I can imagine that I have 4 different scalars, so there's only an S channel process. But it's an important fact, actually, which will recur later, is that if I have massless particles with spin, it's essentially always inconsistent to restrict to a single channel, which is kind of an interesting fact, that having everything propagate consistently often requires you to introduce more than one channel. And there's a concrete way of seeing that from the boundary perspective, which I will tell you in a little bit. But if you're not satisfied, ask me again.
Okay, thank you.
Thanks for the question. Okay, so it turns out actually that the simple examples I've already shown you are completely fixed by these singularities. If you only told me where the singularities are and what their coefficients are, that's actually enough information to uniquely reconstruct the answer. So let me just give you the simplest example. So this 3-point wave function coefficient that I showed you, it just goes 1 over the energy of each particle. And that's trivially the 3-point scattering amplitude divided by the sum of the energies. And so this thing is uniquely fixed by that information. That example is not that exciting, but it's slightly non-trivial for the 4-point wave function coefficient. So on the left partial energy singularity, we know that things have to factorize like this. This is the left partial energy, this thing I was calling E left on the previous slide. This is just 1 over S, the Mandelstam S written in terms of these energy variables. Sorry, that's backwards. Sorry. This is the left energy, K12 plus S. The left amplitude is just 1. This shifted wave function coefficient, if you compute it in this particular example, takes this form. I apologize for the confusion. And then the right partial energy singularity is the same with K12 and K34 flipped, so it looks like this. And then the challenge is to find an object that when you go to the left partial energy pole has this residue, and when you go to the right partial energy pole has this residue. And it turns out this is a non-trivial task because this left residue has a singularity when E right goes to 0. And similarly, this right residue has a singularity when E left goes to 0. And so I can't just add these two things together because I won't get things right. I have to actually find an object that consistently factorizes in the two limits. And it turns out that the right thing to do is to think of this as the total energy evaluated at these two singular loci. And so this is the unique object that has these properties. And in this particular case, it's kind of interesting that you're forced to have this total energy singularity just by demanding consistent factorization. And then the residue of that total energy singularity is precisely the flat space scattering amplitude in the S channel. Okay, so that's kind of just a fun example. Okay, so everything I told you so far is in flat space. And so I need to kind of convince you that similar things should be true in de Sitter space. So I'm not going to rigorously justify this, but let me try to make it sound at least plausible, and then we'll take the logical leap together that what I'm telling you is true. And so roughly speaking, the main technical difference between flat space and de Sitter space is that these flat space plane waves, which are like appear in the bulk to boundary and bulk to bulk propagator, get replaced with Hankel functions. And so that's also one of the reasons why doing these calculations in de Sitter is much harder. And so, of course, these plane waves and Hankel functions are different. And so the precise nature of these singularities can change, but the existence of the singularities is fairly robust. And one way to think about that is, I told you that where these singularities are coming from is sort of the infinite past. And in de Sitter space, we know that if I take a mode and evolve it back in time, what happens is that the mode shrinks. And so in the very far past, this mode feels as though it lives in flat space. And in a very concrete way, you can take this Hankel function object, which I'll call f of k, and expand it in the infinite past limit. And you see exactly, it looks like a plane wave plus some factors of conformal time, and then there's some subleading stuff as eta goes to infinity. And so the fact that these products of plane waves are unsuppressed when energies add up to 0 is still true in de Sitter space, and so these singularities are still present. Okay, so that should sound kind of plausible, although of course, it depends slightly on the details. Sometimes you get logs or other cut-like singularities rather than poles. Okay. And so I'm just going to ask you to take a logical leap with me in the interest of this being a talk, which is to just say, okay, believe me that these singularities are there, and believe me that their residues are the same in de Sitter space that they are in flat space. Let's take that as an input and then see how far we can get using that to try to construct correlation functions. Okay, so maybe now is another good time to ask if there are questions. Okay, great. Good. All right, so just to sort of summarize what I just told you, the sort of takeaway message from this first part of the talk is that, for example, let's focus on the 4-point function or the 4-point wave function coefficient for the time being. This object is singular at 3 points in kinematic space. One is when the total energy involved in the process adds up to 0, and the coefficient of this singularity is a flat space scattering amplitude. Another point is when the energy flowing into the left vertex adds up to 0, and the coefficient of that singularity is a flat space scattering amplitude associated with this left vertex, and then some kind of peculiar shifted wave function thing associated with the right vertex. And then there's also, sorry, this should say, R and L should be swapped here. There's exactly the same singularity with R and L swapped, which I neglected to do on the slide. Okay, so there are these 3 singularities. And roughly speaking, what we want to do is we want to reconstruct the correlation function away from these singular points. So this is sort of the analog of trying to reconstruct the tree level S matrix from knowledge of like its factorization poles. Okay, so a sort of interesting feature, which is kind of recurrent in physics, is that these singularities lie at unphysical configurations. I can't actually access, for example, this total energy singularity in a physical process, which is good because it would be a little bit peculiar if you could measure something infinite in real life. But nevertheless, the existence of these singularities at unphysical kinematic locations control the behavior of the correlator sort of everywhere, even in the physical region. And so here's just kind of a cartoon. So this correlator, if I think of it as a function of how, okay, so this is a cartoon of a 4-point correlator. It depends on 4 momenta, which close into some quadrilateral because of momentum conservation. And I can imagine thinking of the correlator as a function of sort of how squashed this polygon is. And in the physical region, there's never any singularity, but if I allow myself to analytically continue, I could actually access these singularities that I was telling you about. So there are some singularities over here in the analytically continued kinematic domain. But nevertheless, it's sort of like complex analysis. The presence of these singularities over here controls the behavior of the correlator or the wave function for physical kinematics. And so what we want to do is to try to understand how to reconstruct the behavior of the wave function over here from information of its singularities over here. Okay, good. Okay, yeah, so just a comment, I told you that the existence of singularities is robust and that they continue to exist in de Sitter space, but in many cases, the precise singularity structure is more complicated than in flat space. So for example, there can be logs and dilogs and other cuts and stuff. So sometimes these singularities are branch points rather than poles. And in many cases, these singularities can be higher order poles. So here are just two simple examples illustrating this. So this is just the 4-point function of conformally coupled scalars arising from exchange. It has logs and dilogs. And then this is just the 4-point function of some particular derivatively interacting theory, which has higher order poles. So it has like some e⁵ total energy singularity, for example. Okay. And then there's a further complication in de Sitter space, which is very strongly different from the S matrix, which is that the singular loci often don't have the same symmetries as the full wave function or the full correlator. So in the S matrix, the residues at like when particles go on shell are Lorentz invariant. And so it's not very difficult to extend the scattering, the S matrix away from these singular configurations in a Lorentz invariant way. But the locations of these singularities that I just told you about, they're not de Sitter invariant. And typically the residues are also not de Sitter invariant. And so extending away from these kinematic locations in a de Sitter invariant way is challenging. Okay. And so
is there a reason why this truncates at 1/e⁵? Why does it not go higher, right? Via e5, by e⁵?
Oh, it's okay. So this thing is coming from some phi dot cubed interaction. So it's something which has one derivative per field.
Mm-hmm.
And then just as a consequence of, yeah, I mean, these poles are just coming from the factors of conformal time appearing in the interaction. And so if I had more factors of conformal time, I would get a higher power of E.
Oh, okay.
But yeah, it's just because I chose some particular interaction to write this down. It's just meant to be illustrative. You can find other examples with, roughly speaking, if I add more derivatives, I increase the
power
factors of 1/e, very roughly speaking.
Thank you.
Okay, good. Yeah, so I mean, roughly speaking, the goal is we want to extend the correlator or the wave function away from these singularities that I was telling you about. Okay, and so if I have time, I will tell you about two sort of broad philosophies towards doing this, although I suspect I won't have time. The most sort of natural one is like I told you, I have an object where I know what it looks like in some particular configuration. And I want you to tell me what it looks like as I sort of deform that configuration. The natural thing to do is to find a differential equation that controls the strength of correlations as I deform this correlator. And so I will describe how one can do that. And then another interesting idea is that in many cases, sort of in phenomenologically interesting cases, the particles that we're interested in are massless. And so their singularities or their dependence on energies is that they're rational functions. And so having a differential equation to reconstruct these things is a little bit of overkill. And you might imagine that you can kind of glue together objects to construct more complicated processes because they're there are rational building blocks around. And I will sort of try to describe a little bit how you might imagine doing this. Okay, and I should mention Enrico and his friends have also been thinking about this a lot recently. Okay, all right, so this philosophy is sort of probably more in line with the holographic philosophy, which is that what we're going to do is we're going to try to exploit the symmetries of de Sitter space in order to find the differential equation that the wave function has to satisfy. Okay, and so I don't need to remind this audience, but if I have a de Sitter spacetime, the de Sitter group acts like the group of conformal transformations at late times on the future boundary of de Sitter space. I imagine you're all familiar with the de Sitter line element. And so roughly speaking, the fact that bulk de Sitter physics respects de Sitter symmetry implies that the wave function coefficients generated by inflation have the same kinematic properties as CFT correlation functions. So this is exactly the same statement, at the kinematic level that we use to argue that CFT objects should be conformally invariant, or that ADS should generate conformally invariant objects on the boundary. Okay, so just for simplicity, I want to focus on the following process. I want to think about the process in exact de Sitter space, where two conformally coupled scalars exchange a massive scalar field. Or you can think about it as like, a massive scalar field gets generated on shell by the de Sitter expansion, then decays into two conformally coupled scalar fields. And this generates some correlation at late times. So via some arguments that I won't detail for you, you can translate the constraints of de Sitter symmetry along with some simple assumption about the structure of correlation functions in de Sitter space into the following differential equation that this object that I will call F has to satisfy. Okay, so it turns out F satisfies this differential equation, which you can think of as a consequence of de Sitter symmetry plus some assumption about the types of singularities that F can have, which is very closely related to the discussion about these partial energy singularities that we had earlier. Okay, so very roughly speaking, this is a differential operator of hypergeometric type. And when it hits this F, what it does is it generates an object that has only a total energy singularity. So in general, this F will have both a total energy singularity and a partial energy singularities. But there's some operator that when it acts on this F, it generates an object that only has a total energy singularity. Okay. And roughly speaking, you can think of the mere existence of this differential operator, which sort of simplifies the singularity structure, as an avatar of bulk locality. Roughly speaking, what I'm telling you is I have some object that has the singularities of an exchange diagram, and then I have a differential operator that I can act on it with, which generates an object that has the singularities of a contact interaction in the bulk. Okay. And roughly speaking, one way to understand the existence of this operator is that this is a purely boundary manifestation of the fact that the bulk-to-bulk propagator satisfies a Green's function-like equation. That box of the bulk-to-bulk propagator is a delta function. Okay, but it's already kind of neat because you could arrive at this differential equation without ever saying anything about the bulk. It's sort of a purely boundary way of thinking about the fact that interactions happen from the local exchange of a particle in the bulk. Okay, so this is a second order differential equation, and so the natural thing to want to do, okay, it doesn't matter, any differential equation, the natural thing to want to do is to solve it. But this is a second order differential equation, so I need two boundary conditions in order to solve it. And the two boundary conditions that we end up wanting to impose are sort of the following thing. So first, we want to demand that this factorization like partial energy singularity is normalized correctly. And so roughly speaking, we want to make sure this number is correct. As I go to one of the partial energy poles, I get the product of a flat space amplitude times a shifted wave function, which are known objects. And so I can normalize the solution by making sure these objects are normalized correctly. So that's one boundary condition, which sort of sets the scale of the solution. And then the sort of non-trivial boundary condition is that we're going to demand that the singularities I told you about are the only singularities that this object has. So a generic solution to the differential equation I showed you will typically have a singularity in additional location, which can happen for real kinematics. And if you think of this F as a function of 4 points, you can imagine going to the configuration where there's a slight degeneration where this kind of looks like a triangle. And generically, this F will have a singularity there, but you can choose, you can find the solution. This is like a choice of boundary condition that actually this F is totally regular in this configuration. And so that's another boundary condition that we're going to impose. And it turns out this boundary condition is related to the choice of the Bunch-Davies vacuum in the bulk. So similar to if you were doing this calculation explicitly in de Sitter, there's a family of de Sitter invariant vacua. And so similarly here, all of these Fs are de Sitter invariant. but you have to make a choice which selects the adiabatic vacuum. And so this demanding that the singularities I told you about are the only singularities is effectively choosing the Bunch-Davies vacuum. Okay. So here's just some interesting physics. Once you've actually solved this differential equation, what you find is that if I again think of F as a function of the shape of this quadrilateral, this partial energy singularity, sort of at unphysical energy, is a branch point singularity now. And this branch point, or sorry, this branch cut extends all the way to the boundary of the physical region. And so interestingly, it controls the behavior of the wave function as you approach this boundary of the physical region from physical kinematics. And the existence of this branch cut demands that the wave function oscillates as you approach this branch cut. And interestingly, the frequency of oscillations is set by the mass of the exchanged particle. Okay, and you can understand that as being, there's some time delay between so what's going on is we're producing a massive particle in the bulk de Sitter space, which is decaying into conformally coupled scalars. And there's some time delay between the two decays. And roughly speaking, this oscillation is just the ordinary like e to the imt oscillation of a massive particle. And so as a function of the time delay, you see this oscillation imprinted in the correlation. And so this is sort of an interesting piece of physics that if you were able to measure this correlation function in the CMB by looking at the phase of this oscillation, you could extract the mass of the exchange particle. So you could really do some kind of spectroscopy on these objects. Okay, good. All right. So the thing I just told you about is really the simplest possible process. Well, okay, it's maybe the simplest non-trivial process where you really can see the physics of particle creation in de Sitter space. But it was a little bit special in the sense that it had special values for the external masses. They were conformally coupled. And then I was only allowing for the exchange of a massive scalar particle. But you might be interested in more complicated processes. You might want to change the masses of the external particles. You may want to ask about the exchange of a particle with spin. And it turns out that you can very beautifully exploit the connection between these wave function calculations in de Sitter space and conformal field theory in order to leverage some tools that people have developed in the conformal field theory community to generate new solutions to this differential equation that I was showing you. And so roughly speaking, there exists like a whole host of operators that when you act on this sort of simple seed object, which is the 4-point function of conformally coupled scalars exchanging a massive scalar, it can transmute it into a whole host of other processes. So for example, if I want to generate the solution where a massive spinning particle is exchanged, it turns out there's a relatively algorithmic way to do this where I just act with some differential operators on this f function that I described for you, and it generates some non-trivial exchange solution, which is now a function of more kinematic variables, but which really has the same physics of exchange, which is captured by this scalar exchange. And so if you like this kind of thing, there's a completely explicit formula for exchange of basically any mass and any spin, between conformally coupled scalars. Okay, and the thing that's nice about this is it shows that there's really some universal structure to the solutions, which you can kind of see because the kinematics or the singularity structure is really controlled by this seed object, which is the scalar exchange. Okay. So another interesting thing that you might be interested in, which is kind of related to the question that Beatrix was asking, is that we can just as easily act with these weight shifting operators on external particles. And so I can generate for you an object with spinning external fields from a scalar correlator. So for example, if you have a scalar 4-point function, it turns out there's also an operator which will generate for you, for example, a 4-point correlator with an external graviton, okay? But it turns out there's another interesting and important constraint for massless spinning particles in de Sitter. So I told you that correlation functions of scalar fields have to be consistent with de Sitter symmetries, which translate into conformal kinematic ward identities. But massless particles in de Sitter are sort of dual to conserved currents on the boundary. And these conserved currents satisfy additional constraints. So they have to satisfy essentially what are current conservation ward identities. And so they're further constrained beyond just pure kinematics. And so just as a very simple example, if you have like a spin 1 current on the boundary, its longitudinal part is not completely free. Its longitudinal part is fixed in terms of lower point functions, basically by some current conservation ward identity. And so the challenge of computing correlators of massless spinning particles in de Sitter is slightly more constrained in the sense that you have to find objects which both are consistent with de Sitter symmetries and which also satisfy these current conservation ward identities. And you have to solve them simultaneously. And it turns out that in general, this is a non-trivial problem. And in fact, not all possibilities are allowed. So it's very much like in flat space, not all possible S matrices involving massless particles are allowed. There's a really restricted menu of possibilities. And much like for amplitudes, in many cases, this forces us to include chain exchanges in more than one channel. So as a very concrete example, here's the 4-point wave function for Compton scattering in de Sitter space. So you shouldn't worry too much about these kind of peculiar spinor brackets. They're just capturing the helicity information of the external particles. But the important thing is that, this object, the full object, is the only thing that satisfies both the constraints of de Sitter symmetry and current conservation. And notice that it has a total energy singularity, which is sort of common to all of the pieces, but it has a piece which has partial energy singularities in the S channel, and then also a piece which has partial energy singularities in the T channel. So this object comes to you sort of as a sum of some exchange in the S and T channel, and you really require both of these and also an additional contact piece in order to get something which is consistent with all the constraints of de Sitter symmetry. And so it's kind of interesting because this is a way you could rediscover things like charge conservation or the equivalence principle purely from the boundary point of view. And it's kind of interesting because this is a completely irreducible object. It's still not, okay, for the experts, here's like a slightly dissatisfying feature of this object is that it still comes disassembled into something that looks like a Feynman diagram expansion. And so you might dream that there's some way of writing this object that looks nothing like perturbation theory, that it's really some irreducible thing that you can't split up. But that at this point is still slightly a dream. So here I'm just showing you the simplest possible spinning correlator, but you can extend this to more complicated cases. You can compute correlators of gravitons and stuff like that. Okay.
Sorry to interrupt, but we are nearing the end of like the official end.
Yeah, okay. I will end very shortly. Okay, yeah, so I'm just going to actually skip all this stuff. But I'm happy to talk about it if people want to talk about it. And let me just sort of conclude, roughly speaking. Okay, so I think it's fair to say that we're just sort of like starting to apply lessons from holography or make progress in understanding things about cosmology and inflation from the boundary point of view. But I think it's clear we've already learned a lot of interesting things, and it's clear that these techniques can be pushed farther and that there's more to learn. And I think a nice thing about this meeting is that I think in order to make further progress, a very promising direction is to import further insights from both flat space and ADS holography. And so I'm excited to talk with all of you about that. And just sort of as a summary of the things I told you. So there's sort of a very interesting, so if you like amplitudes or you like scattering, things like that, there's already a very interesting reason to care about the wave function, even if you don't care about cosmology, which is that the wave function or correlators are in a very precise sense a deformation of amplitudes. And so it seems clear to me that there will be analogs of all the rich structure that has been seen in amplitudes in cosmology or in the wave function. And we are already starting to see pieces of that, and it's clear there's like a lot more to discover. And I hope I've convinced you that many of the features of the cosmological wave function follows from its singularities. And the interesting thing is that you're trading the challenge of bulk time evolution for the challenge of extending these objects away from their singularities. And just sort of as, you know, some vague speculation, you know, in the spirit of the theme of this conference, like if we really want to understand, you know, one of the reasons we want to do cosmological holography is we want to understand something about the Big Bang, or the very, sorry, not the Big Bang, the initial singularity, or the very earliest times in the universe. And if we really want to do that, probably we require some non-perturbative understanding of what holography means in de Sitter space. And, you know, sort of as an open question is, can we apply some of the lessons that people have learned in ADS to make some progress on non-perturbative holography in de Sitter space? And I should mention there's been some recent work trying to take some steps in this direction. So it'd be interesting to talk about it more. But let me stop there, and I'm happy to take any questions.
Thank you so much for this nice talk. And we can have a couple of questions. You can raise your hand if you want to ask questions. Yes, Costas?
Sorry, I was just clapping hands.
Ah, sorry. Okay, any questions? Okay, I actually have one naive question. In these, like in the first example, conformal coupled scalars and some massive field in the bulk, does it matter if the field is heavy or light? Like if the bulk massive field is heavy or light?
Oh, no, yeah, I think, yeah, you kind of have to treat the two cases separately, but it can be done for either case. In fact, the more interesting case is when it's heavy. That's when you get these oscillations that I was showing you. Yeah, but it can be done for any mass.
Okay, thank you. And if there are no other questions, but I thank you again, and I invite everyone to stop by the Gather Town before calling it a day. Especially, we would like to encourage students to join in the discussions. And thank you everyone so much.